Welcome, my name is Mattia Colombo, and Material Classification for Acoustic Simulations is a short title of the paper that myself, Dolhasz and Carlo Harvey have authored for CHI 2021. Our paper focuses on recognizing materials in acoustic environments. The places shown in these figures, such as the airport in Singapore, Half-Life 2 the computer game, or the Opera House in Italy, have very unique acoustic environments, and among different factors affecting the resulting soundscape are materials, and specifically acoustic materials. We can essentially define acoustic materials as semantics mapped to acoustic information. In the table, for instance, there is glass and glazing associated with alpha absorption coefficients, which is information that acoustic renderers can use to simulate phenomena associated with wave propagation. In our study, we take a conference room. We capture its geometry in a virtual environment using a LiDAR scanner, and we generate acoustic simulations predicting materials with a method that we introduce. This method predicts and assigns acoustic materials in scenes using a system composed of two parts: training and inference. The inference workflow: the appearance of scene objects is analyzed to predict materials and map them to acoustic information. Objects in virtual environments are represented by meshes, whose appearance is determined by image textures. We subdivide image textures into small patches using a superpixel algorithm, providing input to a neural network. The neural network classifies each input patch, determining the semantics which map to acoustic data. As an example, on the left, there is a texture from a scene object subdivided in small patches, and on the right are the predicted semantics associated with each patch. So here, for instance, style is the most recurrent prediction determining the resulting acoustic material. This is an offline procedure that takes an average of 11.2 seconds for each texture, and the accuracy depends on the training process. Here, we take the neural network, which corresponds to the trainable part in the inference workflow, and we train it on a large dataset of surface appearances subdivided in small patches, which define a material space of 36 classes that the neural network can learn to distinguish. And to test the accuracy of the predicted acoustic materials, we introduce a novel evaluation framework, where we take acoustic measurements from the real environment to create a ground truth that we can then use to evaluate acoustic simulation from the virtual reconstruction. We compare impulse responses, which essentially are objective representations of a sound transmission between a source and a receiver in space. And in addition, we simulate a subjective test by comparing oral sessions using a learned metric to measure noticeable perceptual differences between predicted and manually assigned acoustic materials. From the acoustic simulations we generated, we find that predicted materials are perceptually indistinguishable from manually assigned materials. This essentially reduces the time-consuming procedure of assigning materials in large, complex scenes. And to conclude, eliminating camera-based approaches adopted in related work, directly recognizing materials from textures, and novel testing framework for such applications are the contributions of this work. And future directions will expand towards applying the method to a large set of scenes with diverse acoustic environments, as well as extending the system to an end-to-end pipeline for acoustic rendering. So thank you for your attention, and please refer to our paper for further details or get in touch with us.